Welcome back, everybody. Today we're going to go ahead and do a lecture on the video that was released where I was in the field and I diagnosed a 24-year-old Lennox heat pump unit here in Florida, finding a bad TXV, a little low in refrigerant where there's some leaks on the evaporator coil, a couple bad capacitors, and obviously high start amps. So it was a 24-year-old unit. That video is getting a lot of attention. This video is just going to break that diagnostic down a little bit so we can better explain in a more timely manner. Stay tuned. Okay, getting right into it. I'm going to play the video off to my left-hand side, and on my right-hand side, I'm going to, as the video is playing, I might stop it a few times. I'm just going to break down different sections of that video and give you a more detailed explanation of what's going on in my head when I'm diagnosing this, where you should be at when you're diagnosing it, what's going to get you through that call faster, and what are the things that are mostly going to impact the success of that call if we were to make a repair. And then obviously a lot of people are going to have different views on how old the unit is and what should be done. But again, this is the customer's decision. You don't know where they're at financially. You don't know where they're at as far as making this commitment and what their reasons are for. So as technicians, it's our job to ensure that we're doing everything on our end to fully diagnose all the issues that are going to pertain to them keeping that unit. You always have to look at that. I think a lot of technicians in the industry, they wind up just looking for a quick sell, and that's not what people want. And if you're a technician, your job should be, well, what happens if that repair falls back on us? What happens if that customer says, you know what, I'm just not putting any more thought towards replacing this. I'm only going to hang on to the house for about another 6 months. I'm passing it down to a relative. They have the money to replace it. I just need to go ahead and keep this thing running for a little bit longer. Maybe I have $3,000 to $4,000 to spend if that's what it takes. That's much better than replacing it for, however much your company puts it in for. At the end of the day, if that customer were to come back and feel that you're being biased on that, right? They're not going to have a whole lot of faith in you or your company. And you're the face of your company. Maybe you're the only one in your company. Maybe there's many of you in your company, but they're going to look at you and go, you know what? I don't get a good vibe out of that guy. I think that he's just trying to sell me a unit. And it doesn't matter. In your defense, you may say, hey, it's 24 years old. It's got like multiple major issues. Red flag all day long. But it's not your money, and it's not your unit, and it's not your home, and it's not your decision. So there's a lot of things there that you have to look at. Is if that customer did not call a estimator out to their house and ask for a quote on a new unit, then you as the technician have to act like a technician, and you have to first figure out what is it going to take in the event, even if it's a small likelihood that we're going to keep it. What do I need to do? This is what's going to separate you from that next company that may come behind you, and they could be that technician, and that's what that customer is looking for. And you don't know what's going to be said about you, what's going to be said about your company. This is your legacy. This is your reputation. This is who you are. And you may have the best intentions thinking you're helping that customer out. But again, you've got to look at this as this is not my money, not my problem, not my home, not my decision. As a technician, I have to act like a technician, work like a technician, and diagnose like a technician. And in the likelihood that they do wind up fixing it, I have to make sure that we're not going to have to come back right away because there's something that I jumped the gun and missed. So I want to make that very clear and then get into this. I'm going to play the video. I had the volume down so you're not hearing me twice. Basically, I start off in the vehicle, and I just wanted to showcase that I'm there for this very reason that I just explained to you. And then I put my GoPro on and I get out of the truck, and I had no idea what I was going to find. And there's no reason for me to stage a diagnostic. I don't care what the problem's going to be. basically when I do these videos, I want to find these problems as fast as possible. So if I can diagnose in 3 minutes or 5 minutes, which I'm really known to do, and find multiple problems with that length of time, and then make the repairs confidently, then you're probably like that video quite a bit, because you'll see me take a lot of fast steps in doing that. However, when I started looking at this, I clearly started to see right away in the very beginning that there's some serious issues. The first thing I'm looking at is I'm looking at the disconnect box here, because I want to make sure that if I were to pull that disconnect out and put it back in at a later time, I don't want to be blamed if that disconnect just falls apart. I mean, that happens to us quite a bit. And then the second thing I'm just looking for, hey, what size equipment do we have? What type of refrigerant are we looking at? It's an R22. It's a 3-ton 10-SEER Lennox heat pump base series. Builder's grade unit. It lasted 24 years. But I'm going to go ahead and pause the video right here before I get to that thermostat. And I'm going to go back to, if you noticed, when we went and looked at that condenser just at a quick glance. Now, I took this cropped image right in the very beginning of this video. I want you to look at this condenser here. This is not ice, and this is not dirt. All right. Either there was dog urine, or there was chemicals applied to this condenser that kind of ate away, but this condenser is extremely corroded. A lot of the fins are just damaged, and it's a very small 10-SEER unit. It's got that unique footprint that they don't make anymore. And when you look at that heat pump and you see that that condenser is in that condition, the first thing that pops up in my head is, okay, I'm probably not going to be condensing vapor to a liquid very well. And that's the only job that that condenser has when it's in air conditioning mode. And so when I first saw that, I'm going, all right, we'll go ahead and circle back around to that. The next thing I looked at, and I'm going to pull this next image up here, was actually the drain line. I'm going to go ahead and blow this image up. And that was already in that video. I looked at that drain line. There's not a lot of moisture on that ground. And in the video, you can see it drip just a little bit. Those first two indications, when I first walked up to it, made me go, maybe I should do things in reverse order. Typically, you always want to start at the thermostat. Maybe if your customer's home, you want to talk to them, get some details. Then go to your thermostat. Make sure it's functioning properly by dropping the temperature down. Step 3 would be going to the air handler, and then you want to make sure that the fan's running on it. If you're calling for cool, it's got to be running. You want to check the filter, right? Make sure it's not restricting airflow. And you want to also look at that evaporator coil and make sure it's not restricting airflow and it's able to absorb heat. And so you want to make sure there's no CFM issues that you can tell just at a quick glance. Not that I'm measuring, 3 tons of airflow, but I mean, when you do it every day long, you can at least walk up to it and go, okay, yeah, that's pretty loud. It's running, and the coil's clean with a clean filter. Okay, those are very simple observations that you have to be taking typically before you even go to look at that outside unit. However, I wanted to kind of do things in reverse order because I knew it was a 24-year-old unit, and I wanted to make sure that this thing was possibly cooling. So when I saw not much water coming out of the condensate line and the unit not putting out much heat, I checked my, the beer can in it where you touch your suction line and your liquid line, and you're just seeing if things are, not the same temperature, right? Indicating that you have gas and the compressor is running. That vapor line was not cold to the touch at all. And so I already knew right away there's an issue. And it doesn't tell me what the issue is, but I knew enough to know that, okay, there's definitely going to be an issue here. That kind of changed my my momentum a little bit on that diagnostic. I kind of got excited a little bit, but just like we always do, like, oh my God, there's a problem. Let's go look into it. And so as we wound up going inside, that thermostat, on an 85-degree day was literally already in the low 70s when I dropped it down to keep it running. I always want to drop that thermostat down a few degrees, drop it like it's hot so it doesn't satisfy on you. I'm just looking at that air handler and nothing screams at me. Nothing's saying, hey, this is crazy. It's pretty standard setup. And as that video is playing, I'm going to go ahead and shrink down this drain line image. And I'm going to pull that air handler image back into view. And this is pretty much what we're looking at. Okay. And as I saw that, I said, okay, good enough for now. I'm going to go ahead and just quickly throw my gauges on that unit. Now, normally I would not do that until I've already looked at my evap coil, but when I didn't see much of a drip on that drain line and the lines weren't very cold, I'm excited. I want to go ahead and just jump the gun. Let me throw my gauges on this unit. And that's what I did. As I put those gauges on, I realized right away that there was an issue. The moment we saw that the pressure on those gauges were reading too low on the low side and they were reading pretty low on the high side, that was a clear indication that obviously the system is most likely undercharged, and that would back up the drain line not really dripping that much. And so I'm just going to let this play out a little bit. But when I saw that, I'm going, all right, well, it's definitely low on charge, but that doesn't mean that we're done. That doesn't mean pack it up, get a hold of the customer and say, hey, look, you're low on Freon, it's 24 years old, you just got to replace it. That's not what we're going to do, because the moment they say, okay, well, where's my Freon leak at? Or what can we do about it? What are you going to say? Nothing. Just change it. If that's not the answer that your customer is looking for, then you're not meeting your customer where they need you to meet them. I'm going to go ahead and pause it right here. A couple of y'all did a really good job, and I'm proud of you. Some of you are a little mean about it, but that's okay. Technicians can be that way. I have these two reversed. Now, not here. They're hooked up properly. You can see our high side is 175, our low side is 33.7. And it kind of balanced out at 176 and 34. But what I mean by reversed, when we did the editing on the video itself, I must have watched this video 2 or 3 times, and I cleared it. I said, oh, we're good to go. So I apologize and thank you all for catching it. But where we should have caught it was between here and here. These two need to be swapped around. Not at the gauges, just in the description here. We put suction pressure 176 psi and head pressure 35 psi. And some of you said, oh, they're hooked up. They're not hooked up. Wrong. It's just the editing. When we came in and we said 1, 2, 3, 4, here's our values. We just, we didn't pay attention to our wording there. Not a big deal. Things happen, right? But somebody else mentioned something along the lines of head pressure. Do you mean liquid pressure? Guys, I'm going to be very clear with you. Liquid pressure and head pressure, okay? Don't get that confused, all right? And I'm going to get to that in a little bit, but pressure, high pressure is high pressure is high pressure is high pressure is high pressure. It's high pressure. You call it, it's high pressure. You go down the rabbit hole on this technical terminology, and you're going to get so wrapped up and lost in words, you're going to miss your own diagnostics. We don't need to sound super technical. Oh, you mean liquid pressure? Not, guys, it comes off the compressor. It's my high side pressure. It's everything else is irrelevant as to what you want to call it. Okay, coming out of the condenser, yes, it's liquid, but you know what? That's a theory. You have got to prove that that is a liquid. We don't know that. So we're talking about a pressure. So we're just going to call it a head pressure. That's why we have a thing called subcool. Subcool proves that there is liquid, that vapor has condensed. And I'm going to get into all of that on this video. So we needed to switch these around. And you know what? I apologize for that, but hey, we got to move forward and get off of that. I'm going to go ahead and just, I don't need to pull this image back up, so we're going to go ahead and just clear that image off the smart board. I am, however, going to pull up this next image here, which is pretty much the same thing that I cropped off the video without the text on there. It's pretty much like right in here. I'm going to go ahead and stop it. All right. So looking at this here, let me see if I can't blow this up a little bit more. Let's look at those pressures. What can we find wrong with pressures? Okay, well, we're R22, and I'm just going to go ahead and, I hope this shows up. I'm just going to write over this a little bit more. This is 34 PSI. Let me do that a little bit better. We have 34 PSI there. Over here we have 177 PSI. That's already outside of its operating range, okay? That is not enough information to diagnose an expansion valve, a TXV, okay? It's not enough information to even diagnose it being low on refrigerant. We have got to look at our clamps, our subcool, and our superheat values. And when we look at those values, it tells the rest of the story. So I'm going to go ahead and just put it in red, this next one here. We have 4.6 on the subcool. Okay, over here we have 60. I'm just going to round up to 69. So 69 degrees and 4.6 degrees. So if you've seen any of my superheat and subcool videos on how we can learn better how to diagnose mechanical systems based on liquid ratios and vapor ratios, you'll see that I use a cup analogy. That cup analogy is something that I've taught guys for decades, and it has reduced callbacks. It has better made technicians have more confidence when they're trying to diagnose mechanical issues. If you use the superheat and subcool analogy with the cup that I have on this channel, you will see that everything there correlates with a combination of the condenser and evaporator in conjunction with each other, you know, taking that subcool and that superheat. And when you put those two together, those values themselves, I'm just going to kind of make up a percentage, are probably like 85–90% of the values you need to diagnose. The pressures are just not enough information by themselves, but they kind of help assist your superheat and subcool values, right? And so I would say like maybe 90% of your answers are going to come with the subcool, using that in conjunction with the superheat. You know, how do they come together, so we know how to diagnose, and then what are the pressures. It's like saying if I were to diagnose a system with a thermometer and a return, and then take the same thermometer and I put it in the supply air plenum, and if I have a 14-degree split, I'm just going to wrap it up and say that what, I have a bad TXV or I'm low on refrigerant. Is that going to be your diagnostic? I hope not. You're going to say, no, I need to put my gauges on it. And then if you put your gauges on it, you're going to see your high side pressure, your low side pressure. those two in combination are not still enough information. You have got to put like a set of field piece estimates on this thing and really read all the values in conjunction with each other and how they relate. This way, when you add a refrigerant or take refrigerant away, if you add airflow or take airflow away, for example, you'll see in the video I take the blower door and the coil door off. So now I'm not circulating any air across my coil. So my coil's not absorbing any heat. So if I wanted to look at what would that do to my superheat, well, theoretically, my superheat level should drop because my coil will fill up with more liquid. Now, we know there is some liquid in the system because we have a 4.6 degree subcool. Now, typically, if I was to say, well, looking at the suction pressure of 177 versus head pressure of 177 versus suction pressure of 34, then I would say, hey, those two are kind of pointing towards low on refrigerant, right? And then I would say, all right, well, what is my subcool value versus my superheat value? So we want to go high side versus low side, and then we want to look at the subcool versus the superheat. It's always a versus, so in conjunction, they tell a story. This story here, 4.6, does not say that my only problem is low on refrigerant. That says I could be a little low on refrigerant, but there's something else going on. Because 4.6 subcool, that's not terrible. It's really not terrible. But a 70 superheat, that's horrible. That is horrible. And I want to correct somebody who said your superheat should be between 8 and 12. If you're working on a cooler, right, then yes, you're absolutely right. But if you're working on medium temperature, 8 to 12. Low temperature, you should be more between 3 and 8, right, at temp. And then on high temp, like air conditioning, we should be between 12 and 18. That's typically, now somebody might argue and go, no, you need to be 22, and Goodman says 20. Like, come on, forget all that. You're going down the rabbit hole again on those types of things. We need to look at, if you were to take that nameplate off of that condenser because that sunlight bleached it out, what are you going to do? You're going to call the manufacturer and say, hey, I know I'm working on your unit, but I don't have a model serial number for you, and it's working on this air handler that somebody peeled off the sticker or painted it or whatever. I don't have any information to tell you, but because it's a Goodman, what kind of superheater subcool should I have? What answer are they going to give you? They can't give you anything. So you have got to have some type of foundation, some type of principle that when you walk up to a unit and you're putting your gauges on it, your manifolds are telling you a story already. You need to know how to drive that car. How do you get from point A to point B passenger safe? How do you get there? How do you diagnose? You can't always ascertain what is the perfect superheat value and what is the perfect subcool value, because when you've been doing it since 2000, the year 2000, like me, good luck trying to find that perfect superheat and subcool on every single unit, because there's too many variables that are just not going to let you get there. I'm sorry. You might have water in the chase that's warming your superheat up even higher. You might have water in the chase that's really cold because the drain line's just dumping 44-degree water into it, and now your vapor coming back through is condensing to a liquid, giving you a low superheat. Okay, so manufacturer guidelines aren't going to help you with that scenario. You need to be able to steer around that as an obstacle and still provide a service, yet quote what needs to be repaired, right? But still, you can't just shut things down and tell people, sorry, you have no air conditioning. There's nothing we're going to do for you. That's not the world we live in either. So you have got to take ductwork that's maybe undersized because somebody put a half-ton larger air handler in and condenser in 8 years ago. And now you're there and you're looking at a superheat of 10. And you're like, okay, well, it's a 3.5 ton, 1,400 CFMs of air. Well, I only have, you know, a 14 on it. Now, that's only going to give me 1,000 CFM. So I'm already 1 ton air down. That's going to drop my superheat. In conjunction with a dirty filter and a dirty coil, all that will drop it even more, right? Maybe somebody raised the fan speed up, right? That will increase your superheat. And so there are so many things that can change these variables. So you've got to know how to drive the car. You got to know how to drive in the rain. You got to be able to know how to drive on a slick road. You got to be able to know how to drive in traffic, right? You know these things because you do it all the time. Well, when you work on air conditioners and you work on it all the time, there's no difference. You just know how to pick things up and you know how to run with it. And some people are just really good at it, right? And so I want to help everybody get there a little safer, a little bit quicker, right? So your journey's not, 25 years later figuring out that 10 years ago you had it wrong. That happens. It's not a book that you can just buy and open up and it just tells you all your answers. And if you went by that book, then you're going to go into the field and go, well, how come I can't make sense of this? And that's where this channel's beautiful and we're able to share this knowledge. And you can share by hitting that share button now, push it out to your buddies. So this story tells me, yeah, I might be low on charge or something else mechanically is going on there indicating high side pressure, low side pressure in conjunction, maybe a restriction. But when I look over here, I can't say that that's a dryer. I can't say that that's a dryer. And first of all, if you know anything about a Lennox heat pump, the dryer is before the service valve inside the condenser unit, right underneath the outdoor TXV. So we are already measuring the high side pressure, right, after the dryer. So if I have a 4.6 subcool past my dryer, okay, then obviously my dryer is not the issue of why I have a high superheat, all right? And so we also have to be very careful about jumping the gun. And just like we saw in those comments, and please keep leaving them, please, because it allows us to elaborate, talk about it, do something about it, get better, right, by communicating. But when I see some of those comments, the first thing I said to myself was, well, this is a pretty technical person, and I really appreciate that, and I think they're going to really do great in this industry. However, if I went behind that individual and that was on their service invoice and that service invoice said that, I'm going to go take that customer and go, hey, let me educate you real quick. Your dryer is here. I'm reading pressure past the dryer here. This can't be a problem, period. Because I can't read pressure over here on this side of the dryer because the Lennox doesn't give you a hookup. That's a nice thing about working on a package unit. You can actually take your vapor pressure right off the compressor. Then you can take your, liquid pressure, because in theory it's supposed to be a pressure that is of liquid. However, the pressure should never be different unless there's a pressure drop somewhere, right? Like a dryer. But anyways, we didn't have a pressure drop across the dryer because we could not tell in that scenario because the dryer was not outside the cabinet. It was factory installed below the TXV on the outside unit. I'm pointing over here because this is where the condenser is. So this 69 superheat, that's a bad problem. I know my evaporator coil is just starving for Freon. However, it's not starving for Freon because there's just not enough Freon. No, I wish I could only say that. No, it's got enough refrigerant because I condensed. I have proven that I have got liquid. And because I have proven that I have liquid in conjunction with that superheat, now I know that those two in combination more indicate that there is a restriction, right? Now that does not mean that I don't have a restriction plus I'm a little low on charge. That just means that I'm just not only a little low on charge. Because what happens in our industry when techs are like, going to their truck and they're grabbing their gauges and they're coming out there and they're hooking them up. and they see these numbers and they're like, I wonder what's going to happen if I add Freon to it. So what happens is they go grab their Freon, they go over there, and owners of companies and service managers, they just love this. What do? You add Freon to the unit. Why did you add Freon? First of all, the homeowner never gave you permission. They're not going to pay that bill. And you're only sitting there adding Freon because you want to see what happens. Did you take the recovery tank and a scale over there too, so you can scale in 6 or 8 or 10 or 12 or 16 ounces / 1 pound of refrigerant, and then back it out? No, you didn't. You left it in there. And how many times have you gone out there and the other customer says, yeah, the guy said it's got a restriction. You're like, yeah, I bet it does, because now my subcool's no longer 4.6. My subcool's 14.6. And my head pressure's not 177 now. You've made it 300 on an R22. And guess what didn't change? My suction pressure never got above 50. Coil's still hitting 30 degrees. It's going to freeze. And the superheat, it never dropped probably below 45 or 50, because you realized, it's not just low on charge. Oops, it is, in fact, an expansion valve. And that's what I meant. In my video, when you watch it, I say you need to know where you're going to be before you get there. All right? Before you get there would be an example of, you prematurely tell the customer you're low on charge. And they go, okay, I don't really want to put much money into it. Can you just gas it up? And you go, well, it may only last about 3 months, maybe 5 months. If I gas it up, that's not a repair. You're not going to get a warranty, whatever your policy is, right? So you go, okay. Customer sits there. You had this 30-minute conversation. You had coffee. You had pie. Basically, Susie Smith, you're part of the family. She's telling you, hey, come on by for the barbecue on Saturday. That's how that works, right? Techs get loved on by homeowners that can relate and understand them and feel like that person is there for their best interest. Now you're the popular guy in the neighborhood. They're going to refer you and say, hey, use John Doe technician from this company. But then you made a grave error, and all that conversation that you had, you were pretty much betting on that thing was just going to take Freon and that was going to be the end of it. So now you negotiated $700-800 or whatever it is. They love you to death because they're not buying an air conditioner today. What'd you do? You went out there and you added Freon. You're like, well, I'm sorry, I added Freon, but the indoor TXV is just not letting enough of it go through, so you got to replace that valve too. Well, Mr. John Doe, you said that the system was low on Freon. That's it. I know, but I couldn't tell until I started to add to it. That's where I'm going to stop you. You don't ever have to get to that situation. We've been there. You may be there now, and maybe by watching this video, you'll never be there because you haven't been there before, hopefully. So, knowing this is knowing where you're going to wind up. If I know that I'm already reporting with a decent subcool and a high superheat, yes, I might be a little low on refrigerant, but between these two numbers, it clearly shows that I have a restriction, and the only thing between here and that air handler is the expansion valve. That's the only thing that gives you a pressure drop. Right? Dryers aren't supposed to give you a pressure drop, by the way, y'all. Not on residential equipment. Maybe in a cooler, maybe in a commercial package system where they're using capillary tube dryers or something, maybe of that nature. Yeah, but not on these toys that we're working on. That's not how these things are designed. Pressure drops, I'm going to get into that in a second. And what I see, so you can kind of get into my head, and I can show you how I drive my car, and I stay around all the obstacles, and I hit A+ all day long. So I'm going to erase this. Stay tuned. And we're going to get into a couple of more interesting things that I found in that video. We'll go ahead and continue to play that video. And I thought this was interesting. It wasn't totally necessary for me to elaborate on what the inside unit started to look like as I pulled it off. But when I was looking at that, you got your blower, your heat strips, my low voltage over here, the transformer behind it, right? When I saw that, typically you'll see something that has been undone. I'll give you an example. If you look at how these wires are ran and all that, anytime an air handler is installed, things are done in a certain manner. Anytime things are undone and then redone because of a repair, then you can clearly see that somebody's been in there with their big hands and their tools and they've moved things out of the way. Maybe they left a spare part like a transformer or some fuses or something, right? And then as they do that, it doesn't look as clean and as pretty as the day it was installed. So when I saw that, I saw a unit that has ran the gauntlet for 24 years, maybe had a few small repairs done, like on the capacitors and whatnot. You can tell the capacitor is original, right? But at the end of the, or not original, but it's been replaced. But at the end of the day, that's normal. You're going to see that, but nothing major has been done to this thing. I can see that's a factory coil, factory drain pan, blower wheel and motor. Has the ear mounts that Lennox is popular for with their plug. None of that screams we put a lot of money into this thing. So this customer's got a lot of longevity out of this unit. So for them to now have these major issues after 24 years, yeah, I would advise them, if they wanted to, better their situation, hey, let's start all over again. This is a great opportunity. This thing has left you on the side of the road. Don't invest in it. I wouldn't if it were mine. But if they said, I'm sorry, we're going to have to, okay, well, then here's what we're going to have to do. And so I wanted to take a screenshot of that so we could discuss why that was a big deal, because you want to know as much history of that equipment as possible. And that doesn't mean that there's going to be an invoice that customer's just going to hand you and say, hey, read this, here's the history on it. And if they did, you're probably not going to be able to read the handwriting that's on the faded out writing that's on the ticket anyways from 19 whatever, right? And so at the end of the day, you have to be able to look at things and say, okay, well, that motor's been replaced. That's not a factory motor. Okay, well, that cap's, that was probably replaced a year ago. It's still shiny. Maybe weak, but it's still shiny. Oh, the wires up here have been cut and there's 4 or 5 fuses that are blown that somebody left up here. And, oh, they even left their old transformer. Those tell you signs of what that customer or that piece of equipment has been going through. The reason why I say customer or equipment doesn't mean that that customer had that house for 24 years. We don't know. But at the end of the day, you can see that ice on there too. And that line's not even sweating back. That does not mean, and so if I'm not even sweating back, and if with a 4.7 superheat, why is that coil not one block of, not superheat, subcool, why is that coil not a block of ice? If that TXV was not bad, okay, I'd be having so much liquid of that 4.6 go into that coil of subcool that I would have a lot more ice on that. So it's showing me that I have a restriction there, but also, it doesn't confirm that that's my only issue. So we did get a leak detector out and we started to analyze this coil with a leak detector, and I had to put it on a very super sensitive reading to even pick up some refrigerant leaks. That coil is clean. That's me using my cell phone here so I can ascertain better what those fins look like. I'm going to go ahead and take this next image and just blow it up. And so we can see here, that expansion valve is actually right here. Somebody also made a comment. They said, well, your sensing bulb on the TXV, it has to be wrapped up. Yeah, it does. It has to be wrapped up. Because if it's in the airstream, right, then it's going to pick up heat, right? And if it picks up heat, it's going to open the valve because the refrigerant inside the bulb, right, will expand. Hence, expansion valve, thermostatic expansion valve. So temperature makes the valve expand, opening the diaphragm, allowing more refrigerant to get in there. So we obviously want to wrap them up, but Lennox said we don't have to do that, and here's the reason why. if you look, the way this drain pan is, no air circulates in this area. There's zero airflow in this area. Okay? And so now there are some of these valves that are kind of the process tube here is over here to the left-hand side, and then they'll have the sensing bulb on it, right? And then the valves over here and all that, and then yeah, you got to have it wrapped up like a carrier or whatnot, because as the air moves through the coil, it is moving across that sensing bulb, and you want to make sure that bulb's not picking up any additional heat loads other than the heat load that is on the process tube itself. And it also, that bulb needs to be past all the little tubes that come back from the coil that are feeding hopefully refrigerant in a vapor state, not liquid state. And the reason why we look for superheat is because we're looking for a vapor state, but we don't want to have too low of a vapor state or too high of a vapor state. And what I'm talking about here is, if you look here, I'm going to go ahead and just kind of pick a color. That is one of those tubes I'm talking about. Here's another one right here. Here's another one right here. Here's another one right there. So there's only 4 tubes. 1, 2, 3, and 4. Now, if we look at how many tubes are coming off the expansion valve, we have 4, right? We're feeding up here. Let me use a different color. Here's 1. Here's another one. 2. Right? We have another one over here somewhere. Right? And we have another one. I can't really see where it's going, but there's another one in this area somewhere. And so there's only 4 capillary tubes coming off of that expansion valve. Right? You have 2 going to this side and 2 going to this side. And so we're going to feed this coil into 4 sections. So it's one coil, right? 2 halves, but each coil has got an upper section and a lower section. So we're feeding the top side with liquid. We're feeding the bottom side with liquid, the top side on the right with liquid, the bottom side on the right with liquid, and then we're supposed to boil off and come back as a vapor. So we have to make sure we're getting the right amount of refrigerant to that coil. And that valve is the only thing regulating that. And so as we have 4.6 degrees of subcool, proving that our 177 psi is in a liquid state. So that 177 psi is 100% liquid. There is no vapor present leaving that condenser. We know that because we have more than 1 degree of subcool. And we have 4.6 degrees of subcool. So that TXV is not letting that subcool get past it, right? Because if we were low on refrigerant, the TXV would let the subcool, leave the condenser. All that liquid would flow right through that TXV. It wouldn't be bottling it up or anything like that. And if it was low on charge, we would still see a high superheat, but we would see our subcool level would be very low, like 0, right? And so because we didn't have like a 0 subcool with a 70 degree superheat, or a 1 subcool or a 2 subcool with a 70 superheat, we saw almost a 5 subcool, which is pretty good. If you looked at that condenser coil, I'm surprised any liquid was coming out of that condenser coil. That really says, man, if that condenser coil can reduce and reject heat out of that vapor, right, and leave you with liquid refrigerant, that's pretty impressive, right? That's why I was surprised that I didn't have much water coming out of my drain line, and I had a 4.6 subcool. Everything quickly started to point towards there being a restriction, and that's the only point that has a pressure fall. So what do I see when I walk up to a unit? Now, we all know what everybody sees, right? They see an air handler, they see a condenser, and that's pretty much all they see, right? but I don't see that. I see a little bit beyond that. And this has helped me better troubleshoot. And so I want to share that with you. What I see is 4 items. Let's see here. I see 4 items. There we go. I see a condenser coil, a compressor, I see an expansion valve, and I see an evaporator coil. Now, I don't just see them all in one location, but in my head, this is what I'm looking for. My job for my condenser coil is to take a high pressure vapor, reject the heat, leaving me with a subcooled liquid. My job for the compressor is to have a pressure rise. I'm supposed to take a low side to a high side, right? I'm supposed to move the refrigerant. As I move, I pick up the heat of the compression, and so I have a pressure rise here. This is a pressure rise. This is a pressure fall. Pressure rise, pressure fall. Condenser produces liquid, evaporator produces vapor, right? And so the TXV doesn't produce vapor. The compressor doesn't produce vapor. Neither one of them produce liquid. Their jobs are to have a pressure rise, and the other job is to have a pressure fall. Compressor is compressor rise. TXV or metering device is your pressure fall. So my low side is literally right on the other side of that valve. And so if I have 177 and 33 on the other side, I'll just write these numbers down. Let's see, we had 34 degrees here. We had 177, I'm sorry, not degrees, PSI here. 177 PSI here, right? Well, then that means I'm entering my condenser coil at 177 PSI, and I'm going to leave my condenser coil still at 177 PSI. Okay? But I don't know if this 177 PSI that's a vapor here, right? Now my 177 PSI over here, how do I know it's a liquid? Well, the only way I know that this is a liquid is because I read 4.6 degrees, subcool. There's my proof that I have liquid. So you tell me if I'm low on refrigerant charge, how did that happen? All right? I can be a little low on charge, but that's not my only diagnostic. I can't leave off on that note. And so now over here, the way I look at it is I have 177 PSI going into at 4.6 subcool, right? Liquid, okay, going into my TXV, which is where my pressure fall happens, right? Pressure rise, pressure fall. Now, the low side immediately is too low. It's 34 PSI. That is too much of a pressure drop. Way too much of a pressure drop. Okay? And when I look at that and I see my superheat, you know, which this bulb is reading 69 degrees Fahrenheit. It's measuring my superheat is 69 degrees Fahrenheit. So we don't even know what my temperature is on the bulb, but you know, we're basically saying that for me to be at whatever the VSAT is here, right, and the suction line temperature here, that there is a 69-degree difference. And because there's a 60-90-degree difference, that's not even enough refrigerant in this coil to freeze. So yeah, it could be a little low on refrigerant, but I'm not getting enough refrigerant through this TXV. I'm just not getting enough refrigerant through this TXV. Subcool. This is 69 degrees Fahrenheit superheat. And so when I look at these values, I look at a condenser that has probably 80% charge. So I see that maybe it needs a little bit of refrigerant, right? Maybe another couple pounds of refrigerant, right? Whatever it takes to get that up to 225 and that probably to 60 or 65 PSI. Okay, but by the time I add that and get this up to 100% charge, right, from 80% or whatever, what I'm estimating, because I'm not saying it's out, I'm just saying it's a little low, right? But by the time I were to get this to 100%, I don't want to wind up having a 20 degree or 30 degree subcool, you know, because I know my superheat's not going to climb down to 12 to 18 just by adding refrigerant, because this valve is holding it back. So if I wound up seeing that I'm 80% charge here, then I know also that we're sitting with, I would say probably, well, we can't even really determine what percentage of charge we're actually getting in that evaporator coil, but we know it's not 100%. You know, we could probably say that 80%, if that valve was fine, we would be getting 80% in there. But because that valve is holding back refrigerant, we're not even getting 80%. Maybe what we're getting on that coil is more like, you know, maybe 30%, maybe 40%. That coil is just not getting enough refrigerant in it. And so what do I see is I always look at these when I hook my gauges up and I see, okay, there's four things that we need to keep in mind. The evaporator coil, the condition that the fin plates are in, the condenser, the condition that the fin plates are in, right? We have to make sure that things are clean. Past that, we have to know that the compressor is pumping refrigerant, and we have to know that our metering devices are letting refrigerant move through them freely without obstructing too much, like if the diaphragm was closed off and just unable to open that valve and let refrigerant in, right? And so those four things have always got to take place, and then past that, you just have to make sure the system has enough refrigerant in it to make sure it's at full capacity. So with everything moving, pressure rises and pressure falls, and you get the proper amount of heat rejected out of the condenser and the proper amount of heat absorbed on the evaporator, then you will have good superheat ratios. You'll have good suction pressures. You'll have good subcool ratios and good high side pressures, head pressures. And at the end of the day, those are the things that I always look at. But when I look at it that way, I'm able to determine, right? I'm going to go ahead and erase all this. Oops, sorry about that. I'm able to determine all of that based off of my gauges. What are these gauges doing? You know, and like I said in the beginning of the video, this is establishing, you know, nothing but we have gas in the system. We don't know if that gas is in a liquid state. We don't know if that gas is in a vapor state, right? We don't know if that pressure is in a liquid state or that pressure is in a vapor state until we come down here and we start looking at these next values. So you have to look at this as suction and head pressure. We're always comparing the two in conjunction. You got to have both of those values, but that's about 10% of the equation. About 90% of your equation is going to be between your subcool and your superheat in combination. Another thing too, when you look at an expansion valve, let me go off screen for a second and see if I can't pull one out of the box. Okay, so when we look at an expansion valve here, all right, look at this sensing bulb here. I want you to I don't have like a tube or anything like that to really put this up against. You know, I could show you on an evaporator, but this sensing bulb here, if you look at how much contact it's actually making with my stylus here, the percentage, right, is very small. So I'm going to actually show you here. I got a good idea. Let me go ahead and do it this way. So we'll just we'll take a couple of shapes here, and we're going to say that that this is the very edge of the sensing bulb. So this part right here. So like if you're looking at it this way, this would be like the very edge of that. Now I want to go ahead and take this one and say that this is the very edge of my process tube. And now if we were to look at how much area is actually being making contact, it's very small. So if we looked at this in a pie chart, we would say the whole thing would be 100%. That's probably right around, I'm going to assume, maybe 5% and 5% area by volume or less is actually making contact. So there can't be any ambient air around this being affected by the CFMs moving that temperature across the coil and this being in the airstream. Lennox has already put that right above the drain pan and completely out of the way, and they don't wrap them because there's no need for it. So basically the temperature of this pipe and the temperature of the air around it are both going to be the same. So what I'm saying is, if I said that the temperature of this pipe was a VSAT of, say, 44 degrees Fahrenheit, right, then this here should be the same temperature of 44 degrees Fahrenheit, right? So that 44 degrees of heat can expand the gases inside this bulb and allow that gas to come back and open up the diaphragm by pushing against that diaphragm and allowing gas to move through the valve. And only about 5% or less, maybe 3 to 5% of that area is actually making contact. And so what we would want to do, if this was in the airstream, we would want to make sure that there was some insulation around this part here, right? So these two temperatures can be roughly the same without any additional temperatures being added to it that would be what's called a false heat load. And so the one person who left the video saying, oh, it's supposed to be wrapped up, what he's talking about is that. And so it's always a good practice to make sure they're wrapped up, but if it's out of the airstream and it's right above the pan and that's where the manufacturer wanted it, then if you work on Lennoxes, or some manufacturers that do that, Tring does it too, I believe, then you're perfectly fine. You don't need to wrap it up. And that's why they come unwrapped. So it's really unchanged. But it's just very interesting that this bulb here, sometimes you do find them that they're just kind of just floating around. They're not strapped down to that pipe and making good solid connection here. You want to make sure they're always touching. There could be no gap here, because very little percentage actually makes contact, and you need these two numbers to, you need to know that the temperature of this pipe and the temperature of that pipe, I mean, the temperature of this pipe might be, I don't know, I'm going to say, actually, This won't really be 44. If I wanted to run like a 18 degree superheat, then I would be 44 degrees VSAT plus that. So the pipe would actually be 54 degrees, right? No, I'm sorry. I apologize for that. 62 degrees. Yeah. I don't know where I got 54, but it'd be 62 because if I take 62 and 44 and I subtract the two, I get back to 18. And so my pipe is probably 62 degrees. If my VSAT is 44, my superheat is 18, which means that this would actually be 62. And that is enough heat for the gases inside that sensing bulb to heat up and open this valve. But that's not happening. And if you really want to think about it, what proves that superheat being high and there being so much liquid on the other side of that valve is if I have a 69 degree superheat. So imagine that. I have a very low VSAT. I have a 34 PSI. The VSAT to that, I'm going to have to look it up to see what that equals. Go ahead and do this math real quick. It's going to kill me if I don't. Okay. I'm going to go ahead and just look up a pressure temperature chart. R22 pressure temp chart. There we go. And so we have a VSAT, or PSI, excuse me, of 34. Yeah, so that's like 12 degrees. 12 degrees, man. A VSAT of 12 degrees. That's crazy. Yeah, so we know it's not really 12. It's just that's the related temperature to that pressure on R22. We take that 12 degrees, all right, and we had a superheat. Our superheat was 68 degrees. And so we're saying that if we were to add these two numbers up, plus 12, it would be 80. So that means that if we were to clamp that pipe, we're going to read close to like 80 degrees with a clamp, which means that thing is reading about 80 degrees with a clamp because we had a 68 superheat. So if I had 80 degrees here and I'm getting 80 degrees here, that's a lot of heat. Why did my valve that had 4.7 degrees subcool not just open up? That's almost like taking a lighter. It's not 80 degrees, but taking a lighter and just like heating this up or just holding this in the palm of my hand. That valve is going to wind up moving. And so that when I see that high superheat, this is where my brain is at. You know, I go, hey, this coil is starving for refrigerant, and I can't say it's starving for refrigerant because there's not enough refrigerant. I'm saying it's starving for refrigerant because it's a little undercharged, but that valve is not opening up. So if I were to only add refrigerant charge to it, then that valve still got a problem. So I might as well just tell the customer, hey, you know, based off of my findings, we have a little low in refrigerant. We found some small leaks in the system. We can solve that a few different ways, but our valve's not letting refrigerant get through there. We have a couple of weak capacitors, which is pretty common. And we obviously have high start amps, high inrush amps on the compressor, and it's reading LRA on it. It's pretty old. What do you want to do? You know, meet that customer where they're at and see what they tell you. Well, we want to change it. Okay, well, we agree with you. Oh, hey, we want to fix it. I'm like, okay, well, we can do that too. You know, But at the end of the day, there's just so much that goes into a proper diagnostic. There's not one or two values that we can take and go off of. So I don't know what type of gauges that you use, but the gauges that I recommend are basically the Essmans. You don't have to use field piece, but they're a very popular brand, and a lot of technicians have grown to trust them over the years. I've been using them for a long time. I highly recommend them. I trust them. I'm more confident using those and seeing where I'm going to be at. Just their technology, their very accurate values, and it's very easy to find clamps and all types of stuff that you need as you have to keep up with wear and tear, right? But yeah, these compressors, that's going to give me not enough value just looking at high side and low side. And obviously, I can't say that taking the values of only my low side pressure, my high side pressure, and say that, hey, I'm low on charge. That's why I need to know what my superheat and subcool are. But I also can't just take my low side and my high side value and say, I got a bad expansion valve. I can't just say that either. So I need to have more value. So these other, my square, my triangle, they come into play like, hey, this is going to represent my superheat. To me, I look at my evaporator coil, that's superheat. That's all that is. Right? This is all I see here is a pressure drop. That's all I see there. How my brain sees this, all I see this is a pressure rise. Right? So I'll go ahead and correct myself here and say it better. Here's a pressure fall. Right? Pressure. Right? This is a temperature thing. Over here, all I see is a subcool. Right? That's a temperature thing. Right? So I don't care about my pressure on the coil. I don't care about my pressure on the coil. I care about my pressure here. I care about my pressure here. But that pressure rise and that pressure fall versus each other, and that subcool and that superheat versus each other, right? And so here I saw 4.6 to 68 degree ratio. Here I saw 177 psi to 34 psi ratio. And when you get those Essmans out and you can see all those values and how they work, I'm getting more diagnostic here, right? Here's about 10%. Here's about 90% of how I'm going to be able to solve that. Now, just because I'm 90% sure what my problem is going to be, looking at that subcool and that superheat in conjunction with each other, right? I still want to know what my pressure is, right? Because if pressures aren't in the right ranges, or say I had a bad pumping ratio, say my seals were going out on the compressor, and say I had like a high suction pressure. Say my suction pressure was like 100 psi R22, and say my high side was like 140 psi. Okay, well, that right there already tells me that, okay, this pumping ratio is way off. I'm not moving. I have a pressure rise of 40 psi, but I can't trust the values of subcool and superheat with this pumping ratio. So yeah, I'm gonna quickly check my pressures just to kind of see what that pumping ratio is and make sure that they're not too close together and make sure they're not too far apart. But that doesn't really diagnose anything. So that's about 10% of what I'm looking for. I'm in a hurry to hook up those clamps. I got to see what those clamps are doing, because that's when I start looking at liquid and superheat. And as long as I've been doing this accurately with My aim is to never have a callback, and that just happens, right? You get really good, you're just really good. And you can keep things running for 25, 30, 40-year-old units. You keep them running. You're not going out there every 6 months to fix them. You can keep them running for a long time if you do things the right way. Or you can just change it out. But I guarantee you, if you can keep something running for a long time, maybe you need to be looking at that same company and that group of technicians to be installing your next system, because they can keep your old one running for a long time. That means they're going to start that new one up the right way. And that's because they're paying attention to this and they understand that. I hope this video helps you out. I know when we get into these lectures, you know, sometimes you just got to get through it. I don't expect you to get all of this wrapped up and just become a pro out of one video. But, pay attention to the channel. This channel's got a lot of information. We put out a lot of videos. We put out a lot of lectures. Most of our videos are on lectures. We're just now starting to get out there in the field and kind of show you what I'm looking for. And so you're going to see a lot of those. I think the majority of those videos aren't going to be old units that are low on charge and weak capacitors and high starting amps. And on top of that, they have restrictions where valves aren't opening up all the way. I don't think we're going to get that detailed on every one of these. I think most of them are going to be pretty simple. Blown capacitors, or you might get lucky and find some low voltage shorts. That'd be a really cool video to physically show you how fast I can find a low voltage short. So click that notification bell and make sure that when you get notified that next video got released from our channel, you can click to see what that title is to see if it's going to help you crush your next service call. Thank you. As always, stay safe and stay tuned.